Imagine a ship, not a sailboat or a cargo vessel, but the most advanced machine humanity has ever built. A crude starship, crossing the void between our star and the nearest one. 4 1/3 light years of empty space. No port, no rescue, no turning back. Inside, a handful of human beings sealed in a pressurized tube, thinner than an eggshell compared to the darkness around it. Every molecule of oxygen they breathe must be manufactured. Every drop of water must be recycled from their own bodies. Every watt of power must last for decades. And if one critical system fails, just one, there is no replacement, no repair crew, no emergency signal that could bring help in less than years. The ship does not crash. It simply becomes a tomb. If you find this kind of deep science fascinating, a like and subscribe genuinely helps this channel keep going. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. Every story about the future eventually arrives at the same image. A ship. Sleek, enormous, glowing against a field of stars, cutting through the blackness of interstellar space with human beings alive inside it. It is the most powerful symbol our species has ever created for hope. The Starship. Not a branded vehicle, not a company's rocket, not a capsule designed to ferry astronauts to a space station in low orbit and bring them home by dinner. A crude vessel purpose-built to cross the gulf between our star and another one, carrying people who intend to survive the trip. This image has lived in our collective imagination for over a century. It has shaped how we picture the future. It has filled movie screens, launched engineering careers, inspired the founding of space agencies, and embedded itself so deeply in popular culture that most people accept it the way they accept sunrise. Of course we will build starships. Of course humanity will go to the stars. The only real question is when. But before we talk about where the dream leads, we need to talk about the distance. Because the distance is where everything changes. And once you truly understand what interstellar space actually is, measured not in drama but in physics, the Starship stops looking like a vessel of freedom and starts looking like something far more unsettling. A sealed container. A closed machine hurtling through a void so vast, so empty, and so far from anything resembling help that the word isolation doesn't even begin to describe it. Let us start with the destination that every interstellar conversation begins with: Alpha Centauri. It is the nearest star system to our own. 3 stars bound together by gravity. The closest of the 3, Proxima Centauri, sits approximately 4 1/4 light years from Earth. That number is easy to say. It is almost impossible to feel. So let us try. A light year is the distance that light travels in 1 year. Light moves at approximately 186,000 miles per second. In a single second, a beam of light could circle the entire Earth more than 7 times. In 1 year, that beam covers roughly 5.88 trillion miles. Now multiply that by 4 1/4. The distance to Proxima Centauri is approximately 25 trillion miles. 25 trillion miles of nothing. No gas station, no landmark, no atmosphere, no gravity well to shelter behind, no magnetic field to deflect radiation. Just vacuum, a few stray hydrogen atoms per cubic centimeter, and the occasional grain of interstellar dust moving at its own velocity through the dark. Here is what that distance means in human terms. Voyager 1, launched in 1977, is the fastest object humanity has ever sent on a trajectory out of the solar system. It is currently traveling at roughly 38,000 miles per hour, more than 20 times faster than a bullet. And at that speed, the spacecraft would take approximately 75,000 years to reach Alpha Centauri. 75,000 years. Human civilization, everything from the first cities in Mesopotamia to this sentence you're hearing right now, spans roughly 10,000 years. The trip to the nearest star at our fastest current outbound speed would take 7.5 times the entire length of recorded human history. That is why no serious interstellar mission proposal relies on conventional rocket propulsion. To make the journey in anything resembling a human lifetime, a starship would need to travel at a significant fraction of the speed of light. Most credible proposals target somewhere between 5 and 20% of light speed. At 10% of light speed, approximately 67 million miles per hour, the trip to Alpha Centauri would take a little over 43 years. That is technically within the span of a human life. A person who boarded at 25 could arrive at 68. But notice what just happened. The moment we made the travel time survivable, we made the journey itself the problem. 43 years. Not in a city, not on a planet, not in a place where you can open a window or walk outside or drive to a hospital. 43 years sealed inside a machine, surrounded by vacuum, moving through a region of space where the nearest human being who is not on the ship with you is receding at a rate that turns communication into a monologue and rescue into a fantasy. Now let us confront a distinction that most popular science discussions skip over entirely, because it is the distinction that makes interstellar travel fundamentally different from every other kind of spaceflight humanity has ever attempted. The difference between leaving Earth and surviving deep space. Going to space is hard. Nobody disputes that. The engineering required to put a human being in orbit is extraordinary. You need a vehicle that can withstand the violence of launch, the thermal extremes of vacuum, the radiation of the near-Earth environment, and the physiological strangeness of microgravity. You need life support systems that can keep a person breathing, hydrated, fed, and sane for the duration of the mission. You need communication systems, navigation, thermal control, power generation, and the ability to bring everyone home. Every crewed mission in history has operated under one critical assumption. Help is close, not instantaneous, not effortless, but reachable. When Apollo 13 suffered an oxygen tank explosion halfway to the moon in 1970, the crew was in extreme danger. But they were also roughly 240,000 miles from Earth. Mission Control could communicate with them in real time. Engineers on the ground could run simulations, redesign procedures, and talk the crew through a survival plan that brought them home alive. The distance was terrifying but manageable. The lag in communication was barely over a second. The entire rescue unfolded over 4 days. The International Space Station orbits roughly 250 miles above the surface. When a system fails, and systems fail regularly, the crew can consult with engineers on the ground in near real time. Replacement parts arrive within weeks. If a medical emergency exceeds the crew's capability, an emergency return to Earth is possible within hours. The station is never more than a few hours from home. That proximity is not a convenience. It is the reason the station works at all. Every crewed spacecraft ever built, every capsule, every shuttle, every station module has operated within the safety net of Earth's reach. The moon is 1.25 light seconds away. Mars, at its closest, is roughly 3 light minutes away. At its farthest, about 22 light minutes. Those delays are significant. A Mars crew would have to wait up to 44 minutes for a round-trip exchange with mission control. That is a serious operational constraint. It means the crew must be more autonomous, more self-sufficient, more capable of independent decision-making than any previous crew in spaceflight history. But even Mars is local. Even Mars is close enough that a distress call would be heard the same day. The crew would know that someone is listening. Someone, at least in theory, could come. Now extend the timeline. A Starship, 5 years into its journey to Alpha Centauri at 10% of light speed, is half a light year from Earth. A distress call sent at that moment takes 6 months to reach home. Any response, even an immediate one, takes another 6 months to travel back. A full year of silence before you hear a single word in reply, and that reply cannot include a rescue vehicle, because nothing humanity has ever built can catch a ship moving at 10% of light speed and match its velocity in deep interstellar space. The reply is words. Only words. Advice from people who are half a light year away and decades away in any physical sense. 10 years into the journey, the ship is a full light year from home. The communication lag is 12 months each way. 2 years of round-trip silence, 20 years in, and the crew is 2 light years from Earth. The lag is 2 years in each direction. Conversations with Earth are no longer conversations. They are time capsules. You send a message and hope someone reads it 2 years from now. You receive answers to questions you asked 4 years ago. Mission control is not a lifeline. It is an archive. And this is the optimistic version. This assumes the communication system works perfectly for the entire journey. It assumes that the ship's antenna remains correctly pointed at a planet that, from the ship's frame of reference, is now a faint dot indistinguishable from the background stars. It assumes that the power required to transmit a detectable signal across light years remains available for decades. These are not small assumptions. The Deep Space Network, the most powerful communication system humanity operates, can barely maintain contact with Voyager 1, and Voyager 1 is roughly 15 billion miles away. Alpha Centauri is approximately 1,700 times farther than that. At interstellar distances, the ship is alone. Not figuratively, not poetically, physically, operationally, and totally alone. Now let us turn that reality inward. Let us look at the ship itself, not from the outside, not as a gleaming icon of exploration, but from the perspective of the people sealed inside it. Because the moment the engines finish their acceleration burn, which in most mission profiles would last months or even years, the ship enters a coast phase. The engines go quiet. The vessel moves at constant velocity through the interstellar medium. And the humans aboard find themselves in a situation that has no precedent in all of human history. They are inside a pressurized structure. That structure is surrounded by vacuum. The walls separating them from instant death might be a few centimeters of metal and composite shielding. Everything they will breathe for the next 4 decades must be generated inside that structure. Every molecule of oxygen must be produced from recycled carbon dioxide or electrolyzed water. Every liter of drinking water must be reclaimed from humidity, sweat, urine, and wastewater. Every calorie of food must either be carried aboard from launch, which for a crew of even a dozen people over 40 years would require a staggering mass, or grown in onboard agricultural modules that must function continuously for the entire journey without a single season of crop failure severe enough to threaten the food supply. The ship is not a vehicle in any conventional sense. It is a world, a tiny, fragile, engineered world with no weather, no ecosystem, no geological cycle, no natural buffer against systemic failure. Every function that Earth performs automatically for 8 billion people, the ship must perform artificially, mechanically, continuously, and without error, for longer than most human institutions have ever survived. Consider the scale of what is being asked. The biosphere of Earth has been running its chemical cycles for roughly 4 billion years. It has the mass of an entire planet to buffer against disruption. It has oceans to regulate temperature, a magnetosphere to deflect radiation, an ozone layer to filter ultraviolet light, a nitrogen cycle, a carbon cycle, a water cycle, each one operating across a global system of staggering redundancy. When one forest burns, another one grows. When one ocean current shifts, others compensate. The system is not fragile. It is the most resilient life support architecture known to exist. A starship has none of that. A starship is a closed loop with no margin. What the engineers build into it at launch is all it will ever have. There is no forest waiting to grow if the onboard garden fails. There is no backup ocean if the water recycler breaks. There is no second atmosphere if a seal ruptures and pressure drops in a critical module. Every system aboard that ship is a single point in a chain, and the chain is only as strong as its weakest link, and the weakest link has 40 years of continuous operation ahead of it. The International Space Station is the closest analog we have, and the comparison is devastating. The station's environmental control and life support system is the most advanced closed-loop life support technology ever built. It recycles urine and humidity condensate into drinking water. It generates oxygen from water through electrolysis. It scrubs carbon dioxide from the cabin air. It is a genuine engineering marvel. With its most recent upgrades, it achieves approximately 98% water recovery, the highest rate ever demonstrated in space. That sounds close to perfect. It is not. The remaining 2% must still be resupplied from Earth, and the system that achieves that rate depends on filters, catalysts, and processing media that themselves wear out and must be replaced. The station receives cargo deliveries every few months. Those deliveries carry not just water system consumables, but food, spare parts, experimental equipment, clothing, and personal items. Without those resupply missions, the station would become uninhabitable within months. In roughly 25 years of continuous occupation, the station has required thousands of hours of maintenance, hundreds of hardware replacements, and dozens of emergency repairs across nearly every major subsystem. Components that were expected to last for years have failed in months. Systems that tested perfectly on the ground behaved unpredictably in orbit. And every one of those failures was resolved with the same set of tools. Real-time communication with engineers on the ground, spare parts launched from Earth, and the ever-present option of evacuating the crew if the situation exceeded what the station could handle. A Starship would need to exceed even that 98%, reaching effectively 100% recovery with no replacement of the filters and catalysts that make it possible. And it would need to sustain that rate, not for months between resupply visits, but for decades with no resupply at all. It would need to do this while also recycling air, managing waste, growing food, generating power, maintaining thermal control, and handling every other function that keeps human beings alive. And it would need to do all of this with components that were manufactured on Earth before launch and that are aging, wearing, degrading, and accumulating fatigue with every passing year. This is the part that most Starship visions gloss over. In the movies, the ship works, the lights stay on, the air stays breathable, the crew walks down clean corridors and stares out of large windows at the stars. The machinery hums in the background, unseen, reliable, eternal. But machinery is not eternal. Machinery is built from materials that corrode, seals that degrade, electronics that drift, lubricants that break down, and joints that loosen. Every machine ever built by human hands has a lifespan. And the lifespan of a complex integrated system operating in the thermal extremes, radiation environment, and vibration conditions of a spacecraft is not measured in centuries. It is measured in years, sometimes in months. There is a concept in reliability engineering called mean time between failures. It represents the average interval between breakdowns of a system or component under normal operating conditions. For complex mechanical and electronic systems, this number is finite. Always. No matter how well designed the system, no matter how high quality the materials, there is a rate at which things break. On Earth, you fix them or replace them. In low Earth orbit, you consult the ground and wait for a spare part. On a starship crossing interstellar space, you open the storage locker, and if the part you need is not inside it, you begin a very different kind of problem solving, one that ends either in improvisation or in failure. And you will not know which one it is until you try. Think about what it means to carry enough spare parts for a 40-year journey. Every pump, every valve, every circuit board, every sensor, every bearing in every motor and every ventilation fan. Either you carry redundant units, which multiplies the mass of the vessel and the energy required to accelerate it, or you carry raw materials and fabrication tools, which requires the crew to be capable of manufacturing precision components in a microgravity or artificial gravity environment for the entire duration of the trip. Neither option is simple, neither option is guaranteed. And here is what makes this picture fundamentally different from every space mission humanity has ever flown. On every previous mission, failure was dangerous. On an interstellar mission, failure is final. Not because the danger is greater in any single moment, but because the options after failure are zero. There is nowhere to land. There is no station to dock with. There is no abort trajectory that loops you back to Earth. The ship is moving at 10% of the speed of light through empty space, and the only destination is forward. And forward is still decades away. The walls of the ship protect you from the vacuum. The air system keeps you breathing. The water recycler keeps you hydrated. The power system keeps everything running, but those same walls that protect you also confine you. That same air system that keeps you alive also means that if it fails, you suffocate inside a sealed container. That same water recycler is the only thing standing between you and death by dehydration in the most remote location any human being has ever occupied. The Starship is not a freedom machine. It is a survival machine. And the moment you understand that, the entire image shifts. The vessel is not carrying you away from danger. It is carrying you into a situation where every system failure becomes an existential threat. Because there is nothing outside the hole except vacuum, radiation, and distance so vast, it turns every problem into a permanent one. There is a phrase in engineering that describes a design condition where a system must operate without failure for the entire mission duration, because no repair or replacement is possible. It is called operate to failure. It means you use the component until it breaks, and when it breaks, you accept the consequences, because there is no alternative. In most engineering contexts, operate to failure is a last resort, applied to low criticality components where failure is inconvenient but not dangerous. On a starship, operate to failure applies to systems that keep human beings alive. And the consequences of reaching that failure point are not inconvenience, they are death. This is the inversion at the heart of the Starship problem. The same machine that makes interstellar travel possible also makes interstellar failure inescapable. The hole that keeps the air in is the same hole that keeps you locked inside if the air turns toxic. The speed that makes the journey survivable in a human lifetime is the same speed that makes stopping or turning around impossible once the coast phase begins. The distance that defines the mission is the same distance that removes every option for rescue, resupply, or retreat. We have not even talked about radiation yet. We have not talked about what the interstellar medium does to a hull moving through it at 67 million miles per hour. We have not talked about what happens to the human mind when it realizes, truly realizes, that the nearest help is years away at the speed of light and decades away by any physical measure. We have not talked about power, about what it takes to run a fusion reactor for 40 years without a maintenance shutdown. We have not talked about what happens when the crew starts to break down before the ship does. All of that is coming. Because the distance does not just create one problem, it creates a cascade. And each stage of that cascade makes the next one worse. The ship has left Earth. It is accelerating toward the stars. The crew is alive, breathing, healthy, hopeful. Everything works. Everything is nominal. The status boards are green and the mission clock is counting forward. But the clock is also counting something else. It is counting the hours on every pump bearing, every filter membrane, every sealed joint, every reactor fuel rod, every circuit in every computer in every module of the ship. It is counting the radiation dose accumulating in every cell of every crew member's body. It is counting the distance growing between the ship and the only planet that has ever kept human beings alive. And every hour, the margin gets thinner. Not dramatically, not in a way that anyone notices today, or this week, or this month, but the margin is shrinking, and the ship is still accelerating. What happens when the margin reaches zero is the subject of everything that follows. There is a type of aquarium called a sealed ecosphere. It is a glass sphere, completely closed, containing water, algae, tiny shrimp, and bacteria. Nothing goes in, nothing comes out. Light passes through the glass, and that is the only external input. The organisms inside cycle nutrients among themselves. The algae produce oxygen, the shrimp consume the algae, the bacteria break down waste. In theory, the system is self-sustaining. In practice, most sealed ecospheres last between 2 and 5 years before the balance collapses. A slight overgrowth of algae, a bacterial bloom that consumes too much oxygen. One species outcompetes another and the cycle breaks. The shrimp die. The bacteria consume the remains. The water turns cloudy. And then it is just a glass ball full of murky liquid sitting on a shelf. A crude interstellar starship is a sealed ecosphere. It is larger, vastly more complex, and engineered rather than biological in most of its critical functions. But the principle is identical. Nothing comes in, nothing goes out, and every process required to sustain life must run continuously, in balance, for not 2 or 5 years, but 40 or more. The question is not whether the engineers can make it work on day one. The question is whether anything built by human hands can sustain that balance across decades without a single failure severe enough to break the loop. Let us walk through the systems one at a time, not as abstract categories, but as specific chemical and mechanical processes, each with its own degradation curve, each with its own failure mode, and each connected to every other system in ways that turn a local problem into a global one. Start with the air. A human being over the course of a normal day consumes roughly 550 litres of oxygen and produces roughly 500 litres of carbon dioxide. A crew of 12, working, exercising, sleeping, would collectively consume thousands of litres of oxygen daily and produce a corresponding volume of carbon dioxide. On Earth, photosynthesis handles this exchange across a biosphere containing an estimated 3 trillion trees and uncountable trillions of photosynthetic microorganisms in the oceans. On a starship, the exchange must be performed by machinery in a space no larger than a few rooms. The primary method for oxygen generation on the International Space Station is electrolysis. The oxygen generation system splits water molecules into hydrogen and oxygen using electrical current. The oxygen is released into the cabin atmosphere. The hydrogen is either vented overboard, which represents a permanent loss of mass from the system, or routed into a secondary reactor that reclaims some of it. This secondary process is called the Sabatier reaction. It combines hydrogen with the carbon dioxide scrubbed from the cabin air to produce water and methane. The water is fed back into the electrolysis system. The methane is vented. Notice what is happening. Even in this most advanced existing life support system, the loop is not fully closed. Hydrogen is lost, methane is lost, water is consumed and only partially recovered. Each cycle through the system bleeds a small amount of mass into space. On the station, this is acceptable because resupply missions replenish the losses every few months. On a starship decades from any resupply, those small losses are cumulative and irreversible. Over 40 years, the bleed down of consumables from an imperfectly closed loop would eventually exhaust whatever reserves the ship carried at launch. Closing the loop completely requires capturing and recycling every atom. Every molecule of methane that the Sabatier reactor produces would need to be cracked back into carbon and hydrogen rather than vented. Every trace gas released by the crew, the outgassing of materials, the volatile byproducts of cooking, cleaning, and biological processes would need to be captured, identified, and either recycled or safely stored. This is not a theoretical impossibility. The chemistry is known, but the engineering required to perform it reliably, continuously, and at scale for decades without maintenance downtime that exceeds the crew's capacity to survive on reserves does not yet exist. The European Space Agency's Melissa project has been working on bioregenerative life support since 1989. The concept uses interconnected biological compartments, including algae, bacteria, and higher plants, to cycle carbon, nitrogen, and water through a closed loop that mimics a simplified ecosystem. After more than 3 decades of research, the project has produced invaluable knowledge and functional ground-based demonstrators. But no fully closed bioregenerative loop has ever operated autonomously for more than a few months without human intervention to correct imbalances. The biological components are inherently variable. Algae growth rates fluctuate with light intensity, temperature, and nutrient concentration. Bacterial populations shift in response to changes in input chemistry, and the higher plants, the crops that would provide both food and atmospheric oxygen, are subject to disease, genetic drift over successive generations of seed stock, and sensitivity to the microgravity or partial gravity conditions that a starship would impose. Biosphere 2 remains the most ambitious closed ecosystem experiment ever attempted on Earth. Built in the Arizona desert and sealed in 1991 with 8 crew members inside, it was designed to demonstrate that a closed ecological system could sustain human life. It lasted 2 years. During that time, oxygen levels dropped from 21% to approximately 14%, equivalent to conditions at an elevation of roughly 13,000 feet. Carbon dioxide fluctuated unpredictably, crop yields fell short, insect pollinators died off while cockroach and ant populations exploded. The concrete structure itself absorbed oxygen through a chemical reaction no one had anticipated. Supplemental oxygen had to be injected from outside. The experiment was not a failure in the scientific sense. It generated critical data, but it demonstrated, with uncomfortable clarity, that maintaining a closed biosphere is orders of magnitude harder than designing one. Now, imagine running that experiment not for 2 years, but for 40. Not on the solid ground of Arizona with engineers outside who can intervene, but inside a pressurized vessel, crossing interstellar space with no one outside at all. Every lesson Biosphere 2 taught, every unexpected chemical interaction, every population crash, every unforeseen imbalance would have to be anticipated, modeled, and engineered around before launch, because after launch, the only people who can fix it are the people trapped inside it. The air system alone is a chain of interlocking chemical processes, each dependent on the others, each with its own points of fragility. But the air system does not operate in isolation. It is coupled directly to the water system, because electrolysis requires water, and the Sabatier reaction produces water, and the crew exhales water vapor that must be condensed and recaptured. If the water system degrades, the air system degrades with it. Water recycling on a starship requires not just recovering liquid from humidity and waste, but purifying it to a standard that is safe for human consumption, equipment cooling, and electrolysis feedstock over decades. Every pass through the recycling loop introduces the possibility of contamination. Dissolved organic compounds accumulate. Microorganisms colonize surfaces and form biofilms that clog filters, corrode pipes, and release metabolic byproducts into the water supply. On the station, biofilm formation in the water processing assembly has caused repeated operational problems. Microbial growth in storage tanks has required biocide treatments and manual flushing, procedures that depend on cleaning agents and spare filtration media supplied from Earth. On a starship, there is no external supply of biocide. There is no warehouse of replacement filter cartridges. The water system must either be designed to prevent biofilm formation entirely, which no water system in human history has achieved in a warm, pressurized environment over decades, or it must carry the means to continuously combat it using only materials that can themselves be recycled or regenerated aboard. Every antibacterial treatment is a consumable. Every filter has a lifespan. Every membrane in every purification module degrades with use, and the degradation products enter the water they were supposed to clean. The thermodynamic reality of water purification adds another constraint. Distillation requires energy. Reverse osmosis requires pressure, which requires energy. Even passive filtration requires periodic backflushing, which requires energy. The water system is not just dependent on the air system, it is dependent on the power system. And the power system has its own mortality. Every serious interstellar propulsion study identifies nuclear energy as the only viable power source for a crewed mission lasting decades. Solar panels are useless beyond the outer solar system. Chemical fuel cells would require more fuel mass than the rest of the ship combined. Only nuclear fission, or if the technology matures, nuclear fusion can provide the sustained power output needed to run life support, propulsion control, communications, lighting, computing, thermal management, and all the other electrical loads aboard a vessel carrying human beings for 40 years. Consider fission first, because fission is the technology that exists today. A nuclear fission reactor generates heat by splitting heavy atomic nuclei, typically uranium or plutonium. That heat is used to drive a turbine or a thermoelectric generator, converting thermal energy into electricity. Terrestrial fission reactors are designed for operational lifetimes of roughly 40 to 60 years. But that figure comes with a critical caveat. Terrestrial reactors undergo scheduled maintenance shutdowns. Fuel assemblies are periodically replaced. Cooling systems are inspected, repaired, and overhauled. Control rod mechanisms are tested and serviced. Reactor pressure vessels are monitored for radiation-induced embrittlement, a process where sustained neutron bombardment gradually makes the metal less ductile and more prone to cracking. A Starship reactor cannot be shut down for maintenance without shutting down the life support system it powers. There is no external power grid to keep the lights on while the reactor is serviced. Even if the vessel carries batteries or backup fuel cells for short-duration maintenance windows, those reserves are finite and intended for emergencies. A reactor that must run continuously for 40 years without a full maintenance cycle is operating under conditions that no terrestrial reactor has ever demonstrated. Fuel depletion is one concern. Neutron damage to the reactor vessel is another. But the more insidious threat comes from the secondary systems that support the reactor. Coolant loops, heat exchangers, turbine bearings, electrical generators, control electronics. Each of these is a mechanical or electronic component with its own failure distribution, and each of them is operating in an environment where radiation levels are elevated. Thermal cycling is continuous, and vibration from the ship's structural dynamics is ever present. Fusion would be better in some respects. Fusion fuel, typically isotopes of hydrogen, is lighter and more energy dense than fission fuel. A fusion reactor could theoretically operate for longer periods on less fuel mass, but no fusion reactor has ever achieved sustained net energy production on Earth, let alone in the radiation-hardened, vibration-tolerant, maintenance-free configuration that a Starship would require. As of the current state of the science, fusion remains a candidate technology, not a deployable one. And even if it becomes deployable, the engineering challenges of running any reactor for 4 uninterrupted decades remain. When the power system degrades, everything degrades. Life support consumes power. Water recycling consumes power. Food production, if it involves artificial lighting for crop growth, consumes enormous amounts of power. A single square meter of crop canopy requires roughly 50 watts of photosynthetically active light. To feed a crew of 12 for 40 years, the agricultural module would need hundreds of square meters of growing area, consuming tens of kilowatts of lighting alone. Add ventilation, irrigation, nutrient monitoring, and pest management, and the agricultural power budget rivals the life support budget. If the reactor's output drops by even 10%, the crew must choose what to cut. Less light means less food. Less power to water recycling means less clean water. Less power to the carbon dioxide scrubber means rising carbon dioxide levels in the cabin atmosphere, which causes headaches at low concentrations, cognitive impairment at moderate concentrations, and loss of consciousness at high concentrations. But the power budget for food production is only the beginning of the agricultural problem. The deeper question is whether a starship can grow enough food to keep a crew alive, healthy, and psychologically functional for 40 years, using nothing but the seeds, soil media, nutrients, and equipment it carried at launch. The caloric math alone is daunting. A moderately active adult requires roughly 2,000 to 2,500 calories per day. For a crew of 12 over 40 years, that is approximately 420 million calories. Carrying that quantity as pre-packaged food would require a staggering mass of preserved rations, each with its own shelf life limitations. Freeze-dried food degrades. Nutrient content diminishes over time. Fats oxidize. Vitamins break down. The shelf life of most space-rated food products is measured in years, not decades. After 10 or 15 years, even the best preserved supplies would be nutritionally depleted. Their textures altered, their caloric density reduced. A crew relying solely on stored provisions would face progressive malnutrition long before the halfway point. This is why every serious interstellar mission concept includes onboard agriculture. The ship must grow food, not as a supplement, as the primary source of sustenance for the entire crew for the entire mission. And growing food inside a sealed vessel moving through interstellar space is a problem of a fundamentally different kind than growing food on Earth. On Earth, a farm operates within a biosphere that provides free services so vast they are nearly invisible. Sunlight arrives without cost. Rain falls without machinery. Soil contains billions of microorganisms per gram, cycling nutrients and suppressing pathogens. Pollination happens through wind and insects. Pest control is partly handled by predator species. Genetic diversity in wild populations provides a reservoir from which crops can be refreshed. A Starship agricultural module has none of these. Light must be generated electrically. Water must be delivered through irrigation systems that draw from the same recycling loop the crew drinks from. Soil, if soil is used at all, must be a manufactured medium whose microbial community is deliberately cultivated and maintained, and that microbial community is fragile. In a closed system, bacterial and fungal populations drift. Beneficial species can be outcompeted by opportunistic ones. A single fungal blight that would be a manageable nuisance on a terrestrial farm, treatable with commercially available fungicides and replaceable seed stock, becomes a potential catastrophe in a module where the fungicide supply is finite and the seed stock is all that exists. Seed viability is its own problem. Seeds are biological material. They age. Their germination rates decline over time, influenced by temperature, humidity, and radiation exposure. On Earth, seed banks maintain viability under optimized storage conditions, and even then, most crop species show significant germination decline within 10 to 20 years. A Starship carrying seed stock for 40 years of agriculture would need to cycle through successive generations of crops, saving seeds from each harvest to plant the next. But each generation introduces the possibility of genetic drift, reduced vigor, and the gradual loss of traits that were selected for productivity, disease resistance, and nutritional content. The nutritional dimension is particularly insidious because its effects are slow and cumulative. A diet that provides adequate calories but lacks diversity in micronutrients will not kill the crew in a week or a month. It will weaken them over years. Iron deficiency causes fatigue and cognitive impairment. Vitamin C deficiency leads to scurvy, a disease that humanity solved centuries ago on Earth, but that becomes relevant again inside a sealed vessel where the only source of ascorbic acid is whatever the onboard garden produces. Vitamin D deficiency, already a concern for astronauts in low Earth orbit who receive limited sunlight, becomes a certainty for a crew that will never see natural sunlight again for the rest of the mission. Calcium and vitamin K deficiencies accelerate the bone density loss that microgravity or even partial artificial gravity already promotes. Each of these deficiencies, taken individually, is manageable with supplements. But supplements are consumables. They have shelf lives. They occupy mass that must be launched and accelerated. And if the crop system falters, if yields drop because the lighting degraded, or the soil microbiome shifted, or a blight wiped out the leafy greens that provided most of the crew's folate, the supplements become the primary nutritional safety net. A safety net that is finite. A safety net that was never intended to replace the agricultural system for years at a time. And then there is the psychological dimension of food. Human beings do not eat merely for calories. They eat for comfort, for social bonding, for a sense of normalcy. Meals are among the most powerful rhythms in daily life. On the International Space Station, crew members consistently report that mealtimes are one of the most important morale-sustaining activities aboard. The variety, the flavor, the ritual of sharing food are psychological anchors in an environment stripped of most earthly comforts. On a starship where the crop rotation has narrowed to 3 or 4 hardy species that tolerate reduced light, where the same potatoes and soybeans and leafy greens appear at every meal for years on end, the loss of dietary variety becomes a loss of morale that no rational argument can compensate for. The crew knows they should be grateful the food exists at all. They eat it anyway. And the slow grinding weight of monotony adds one more layer of psychological erosion to a crew already under siege from every other direction. Food is not a secondary system. It is life support. It is medicine. It is psychology. It is morale. And it must function continuously for 40 years, using biological processes that are inherently less predictable than mechanical ones. Inside a closed vessel where every input is finite, and every failure has nowhere to go but inward. There's a system that no Starship design document can omit, and no engineering diagram can fully represent, because it operates at the intersection of biology, chemistry, psychology, and improvisation. The Starship must be its own hospital. On Earth, a person who develops appendicitis drives to an emergency room. A surgeon operates. The patient recovers in a facility surrounded by nurses, antibiotics, and a supply chain that can deliver any instrument within hours. The infrastructure behind it is vast, distributed across cities, factories, and centuries of accumulated medical knowledge. On a starship, a person who develops appendicitis lies down on a table in a small medical bay. The operation is performed by a crew member who received surgical training before launch, but who is not a career surgeon and who may not have performed this specific procedure in years. The anesthesia is drawn from a supply that must last the entire mission. The antibiotics come from a pharmacy that cannot be restocked. The surgical instruments are the only set aboard. If a complication arises that exceeds the crew's medical capability, there is no specialist to call who can arrive in time to matter. There is no medical evacuation. There is no second opinion that can be delivered within the window that the emergency demands. Appendicitis is one of the simpler scenarios. Consider a traumatic injury, a broken femur from a fall in the artificial gravity section, a deep laceration from a maintenance accident, a severe burn from a coolant leak. Each of these requires not just acute treatment, but rehabilitation, and rehabilitation in a confined, low-resource environment is slow, painful, and incomplete. A crew member who cannot work for weeks or months due to injury places additional load on every other crew member, increasing their fatigue, their maintenance burden, and their psychological stress. Then, consider the conditions that the mission itself will produce. The radiation that awaits them beyond the heliosphere will cause cancers, not hypothetically, statistically. Over 40 years of galactic cosmic ray exposure, some crew members will develop malignancies. On Earth, cancer treatment involves surgery, chemotherapy, radiation therapy, immunotherapy, and access to diagnostic imaging equipment that weighs tons and requires specialized facilities. A Starship cannot carry a linear accelerator. It cannot carry a full chemotherapy pharmacy with the range of agents required for different cancer types. It can carry a limited surgical capability, a limited supply of broadly applicable drugs, and the knowledge of its crew. For some cancers, that will be enough. For others, it will not. And the crew will know this from the first day of the mission. They will know that the radiation striking their bodies is planting seeds that may grow into conditions the ship cannot treat. Pharmaceuticals have shelf lives. Most drugs degrade over time, losing potency as their active compounds break down through oxidation, hydrolysis, or photodegradation. The shelf life of a typical oral medication under controlled storage conditions is 2 to 5 years. Some can be extended with careful formulation and packaging. But no drug has been certified for 40 years of storage in a radiation environment aboard a spacecraft. A crew member who needs a specific antibiotic in year 30 may find that the supply, carefully preserved since launch, has degraded to a fraction of its original potency. The drug exists. The molecule has changed. The treatment fails. Dental emergencies sound mundane until you imagine them aboard a starship. A cracked tooth. An abscess. On Earth, a dentist resolves these in an afternoon. On a starship, they are handled by whichever crew member received the most dental training, using equipment that cannot be replaced. An untreated dental abscess can become a systemic infection. A systemic infection in a closed environment with a limited antibiotic supply is a life-threatening event. The medical system aboard a starship is not a hospital. It is a triage station. It can handle some emergencies, manage some chronic conditions, and alleviate some suffering. But it cannot do everything a hospital does. And the gap between what it can do and what the crew will eventually need it to do will widen as the mission progresses, as the crew ages, as the radiation dose accumulates, and as the pharmacy depletes. Every medical intervention consumes a resource that was finite at launch, and that becomes more finite with every use. And every medical condition that exceeds the ship's capacity to treat becomes a condition that the crew must simply endure inside a sealed vessel with no possibility of evacuation to a facility that could help. This is the architecture of a cascade failure. A single degradation in one system propagates through every system connected to it. And on a starship, every system is connected to every other system because they all share the same power source, the same atmosphere, the same water supply, and the same crew. Let us talk about thermal management, because it is the system that almost no one outside of spacecraft engineering thinks about, and it is one of the most unforgiving. A starship generates heat, the reactor generates heat, the life support equipment generates heat, the crew generates heat. Every electronic system, every motor, every lighting fixture, every computation performed by every onboard computer generates heat. In the vacuum of space, there's only one way to reject heat: radiation. There is no air to carry it away. There is no ocean to absorb it. The ship must radiate its waste heat into space through large surfaces called radiators. Radiator panels are exposed to the interstellar environment. They face the vacuum. They are subject to micrometeoroid impacts, radiation damage, and thermal cycling as the ship rotates or as equipment loads fluctuate. Over decades, radiator surfaces degrade. Their emissivity, the efficiency with which they radiate heat, decreases as the surface materials are eroded, pitted, or chemically altered by exposure. If the radiators lose efficiency, the ship's internal temperature rises. Rising temperature stresses electronics, accelerates chemical degradation of materials, increases the metabolic load on the crew, and reduces the efficiency of the very life support systems that are already operating at the edge of their design margins. There is no way to replace a radiator panel during an interstellar crossing. If the ship is rotating for artificial gravity, exterior maintenance becomes extraordinarily dangerous. If the ship is in zero gravity, the crew must perform extravehicular activity in interstellar space, exposed to cosmic radiation and micrometeoroid flux, with no planetary magnetosphere for protection. Either way, the repair is difficult, dangerous, and limited by the materials and tools available aboard. Every system described here has one thing in common. It was designed, manufactured, and tested on Earth, installed in the ship before launch, and expected to function for a duration that exceeds the demonstrated lifespan of any comparable system in spaceflight history. The longest continuously occupied spacecraft is the International Space Station, where it has been crewed since the year 2000. Every year of the occupation has depended on a global network of engineers diagnosing problems from the ground, a fleet of resupply vehicles delivering spare parts and consumables on a schedule measured in weeks, and the constant option of crew evacuation to Earth if a situation exceeded the station's capacity to manage. That support structure is not a luxury. It is the reason the station still functions. Remove all of it. Extend the timeline by a factor of 2. Seal the system so that nothing enters and nothing leaves. And ask it to keep 12 people alive. That is not an engineering problem in the conventional sense. It is an endurance test imposed on machines by distance. And the distance does not care how well the machines were built. It simply waits. There is a phrase used in long-duration spaceflight planning that captures this reality with uncomfortable precision. It is called logistics closure. It refers to the degree to which a mission can sustain itself without external supply. A mission with 0% logistics, closure carries everything it needs and resupplies nothing. A mission with 100% logistics closure manufactures, recycles, or regenerates everything it needs from resources already aboard. The International Space Station operates at roughly 50 to 60% logistics closure for water and air combined, depending on how the accounting is done. The rest comes from Earth. No crewed mission in history has achieved 100% logistics closure for any critical consumable. Not for water, not for air, not for food, not for spare parts. The theoretical frameworks exist. The component technologies are advancing, but the integrated, demonstrated, end-to-end proof that a sealed system can keep humans alive indefinitely without external input has never been produced. And indefinitely is a word that conceals a brutal requirement. It does not mean the system works most of the time. It does not mean the system works with occasional interruptions that are recoverable. It means the system never fails in a way that cannot be corrected by the crew using only the resources aboard. Never across 40 years of continuous operation in an environment that is actively degrading every component in the system. A pump that seizes in year 27. A seal that develops a microscopic crack in year 31. A catalytic bed that loses reactivity in year 19 because the catalyst material has been slowly poisoned by a trace contaminant that was present in the feedstock at parts per billion concentrations and accumulated over 2 decades to a level that inhibits the reaction. These are not dramatic failures. They are quiet ones. The kind that do not trigger alarms on the day they begin. The kind that show up as a slow decline in system performance, a fraction of a percent per month, a gradual drift that is easy to rationalize, easy to defer, easy to assume will stabilize. Until it does not stabilize. Until the performance curve crosses a threshold below which the system can no longer maintain the conditions required for human survival. And on that day, the crew opens the maintenance log and realizes that the trend has been visible for years. That the decline was always there, written in the data, predictable in retrospect. But by the time the prediction matters, the ship is more than 3 light years from the nearest replacement part, and the only fabrication shop in existence is a small machine bay bolted to the lower deck of a vessel where the lights are beginning to flicker. The ship does not need to explode to fail. It does not need to be struck by a catastrophic event. It just needs time. Enough time, and every closed system reaches the limits of its design. On Earth, you replace the system. In low orbit, you call for a resupply. On a starship between the stars, you live with the decline until the decline becomes the thing that kills you. Consider what this means for the crew in concrete terms. In year 1, the water tastes clean, the air smells fresh, the temperature is comfortable, and the food grows on schedule. In year 10, the water has a faint mineral taste from accumulated dissolved solids that the filtration system no longer fully removes. The air carries a slight chemical undertone from outgassing materials that the trace contaminant scrubber handles at reduced efficiency. The crops in the agricultural module produce slightly less yield per cycle because the lighting array has lost a few percent of its output as the diodes age. None of these changes is dangerous. All of them are real. In year 20, the mineral taste is stronger. The trace contaminant scrubber has been partially rebuilt using spare components, but the rebuild is not as effective as the original. The agricultural module has shifted to hardier crop varieties that tolerate lower light levels but provide less nutritional diversity. The crew's diet is adequate but monotonous. The reactor's output has declined enough that non-essential systems are power cycled to reduce load. Movie nights in the common area are shorter because the display draws power that the carbon dioxide scrubber needs. In year 30, the water recycler is operating at 85% recovery instead of its original 98. The missing 13% is drawn from reserves that were intended for emergency use. The reserves are finite. The crew calculates how many months of supply remain and begins rationing. The air system is functional, but the oxygen partial pressure is slightly lower than nominal because the electrolysis unit's electrode surfaces have degraded and the reaction rate has dropped. The crew feels slightly more fatigued than they used to, but they have been fatigued for years, and the baseline has shifted so gradually that no one is certain whether the cause is atmospheric, psychological, or simply age. This is not a catastrophe, it is a slope, and the slope only goes in one direction, because every component aboard the ship is older today than it was yesterday, and tomorrow it will be older still, and the destination is still years away. What has not yet been addressed is what exists outside the hull during all of this. Because while the ship is slowly aging from within, the interstellar environment is simultaneously attacking it from without. And the nature of that attack is not what most people imagine. The void between stars is not truly empty. It is filled with hazards that do not announce themselves with sound or light. They arrive silently, invisibly, and continuously, and they have been striking the hull since the moment the ship left the heliosphere. What those hazards are, what they do to both the ship and the crew, and why they become more dangerous with every passing year is where this story turns from engineering into something closer to a siege. The moment a starship crosses beyond the heliosphere, the protective bubble of charged particles that our star pushes outward into space, it enters a radiation environment unlike anything human beings have ever endured. Inside the heliosphere, the solar wind provides a partial shield against the most energetic particles arriving from the galaxy at large. It is not a perfect shield. Astronauts aboard the International Space Station still receive significantly more radiation than the average person on the ground. But the heliosphere deflects a meaningful fraction of the highest energy cosmic rays, the ones that do the worst biological damage. Beyond it, that shield vanishes, and there is nothing to replace it for the next 4.25 light years. Galactic cosmic rays are not what most people imagine when they hear the word radiation. They are not the gentle warmth of sunlight or the invisible hum of a medical X-ray. They are atomic nuclei, mostly protons and helium nuclei, but also heavier elements stripped of their electrons and accelerated to velocities approaching the speed of light by the shock waves of ancient supernova. Some of these particles carry the kinetic energy of a fast-pitched baseball, compressed into a volume smaller than an atom. When one of these high-energy heavy ions strikes a human cell, it does not merely ionize a single molecule the way a medical X-ray might. It carves a track of destruction through tissue, breaking chemical bonds along a path that can extend through multiple cells, shattering strands of DNA, damaging mitochondria, and triggering chains of oxidative stress that continue causing harm long after the particle itself has passed through the body and exited the other side. This is not a speculative concern, it is a measured one. NASA's Space Radiation Laboratory has spent decades studying the biological effects of heavy ion radiation using particle accelerators that simulate the galactic cosmic ray environment. The findings are consistent and sobering. Chronic exposure to simulated galactic cosmic rays produces measurable cognitive impairment in animal models. Researchers have documented reduced memory function, impaired decision-making, increased anxiety-like behavior, and structural changes in the hippocampus, the brain region most critical to learning and the formation of new memories. One study estimated that during a deep space mission, approximately 1 in every 3 crew members could experience measurable memory impairment from radiation exposure alone. Another found that roughly 1 in 5 could develop anxiety-like behavioral changes. These are not injuries you can see. They are not injuries the crew would necessarily recognize in themselves, because the onset is gradual and the symptoms overlap with fatigue, stress, and the normal psychological toll of long-duration confinement. A crew member whose cognitive function is declining by a fraction of a percent per month might not notice for years, but the mission depends on that crew member's judgment, their ability to diagnose faults, to calculate trajectories, to perform maintenance procedures with precision, and to make sound decisions under pressure. If the crew's collective cognitive capacity is being slowly eroded by radiation, the ship's effective operational margin is shrinking even when the hardware is still functioning. Then, there is the cancer risk. Galactic cosmic rays are among the most potent carcinogens known. The cumulative dose received during an interstellar crossing at 10% of light speed, even with the best shielding currently conceivable, would far exceed the career exposure limits that NASA imposes on astronauts. Those limits exist for a reason. They represent the threshold beyond which the probability of radiation-induced fatal cancer becomes unacceptably high by the standards of occupational health. An interstellar crew would blow past those limits within the first few years of the journey. By the halfway point, the cumulative dose would be in territory where no long-term human health data exists, because no human being has ever been exposed to that much deep space radiation. Shielding helps, but it does not solve the problem. Heavy ion radiation is extraordinarily difficult to stop. Low-mass materials like polyethylene and water are more effective per kilogram than metals, because high-energy particles striking heavy nuclei produce showers of secondary radiation, additional particles generated by the impact that can be as damaging as the original. This is called secondary particle production, and it means that adding more metal shielding can actually increase the radiation dose to the crew rather than decrease it beyond a certain thickness. The optimal shielding strategy involves lightweight, hydrogen-rich materials, and even then, a practical shield capable of reducing galactic cosmic ray exposure to safe levels would need to be meters thick and would add enormous mass to the vessel. Mass is the fundamental currency of spaceflight. Every kilogram of shielding must be accelerated to 10% of light speed and decelerated at the destination. Adding the shielding needed to protect a crew against 40 years of galactic cosmic ray exposure could double or triple the ship's total mass, requiring proportionally more fuel, which adds more mass, which requires more fuel. This is the tyranny of the rocket equation applied to radiation protection, and it has no clean solution with current or near-future technology. So the crew takes the dose. Year after year, particle after particle, their bodies absorb the damage, and the damage accumulates, and the ship keeps flying. But radiation is not the only thing striking the hull. There is something smaller. Something that most Starship designs acknowledge in a footnote and then move past. Because fully confronting it makes the engineering problem feel nearly insurmountable. Interstellar dust. The space between stars contains roughly 1 atom of hydrogen per cubic centimeter on average, along with trace amounts of helium and heavier elements. It also contains microscopic grains of solid material, silicates, carbon compounds, and ice particles, ranging in size from fractions of a micrometer to occasionally a micrometer or more. At rest, these particles are harmless. They have been drifting through the interstellar medium for millions or billions of years, each one a tiny mote of primordial chemistry left over from ancient stellar processes. At 10% of the speed of light, they become weapons. The kinetic energy of an object is proportional to the square of its velocity. When you increase the speed of an impact by a factor of 10, the energy increases by a factor of 100. A grain of interstellar dust, 1 micrometer in diameter, far too small to see with the naked eye, striking a surface at 10% of light speed carries approximately half a joule of energy. That may sound negligible. It is not. Half a joule concentrated in a volume smaller than a blood cell produces an impact that vaporizes the grain and a small volume of the surface it strikes, creating a microscopic crater and a flash of plasma. One such impact is trivial, but the ship is not encountering 1 grain. It is flying through a medium that contains these particles at a density that, over a cross-sectional area of hundreds of square meters and a journey spanning 4.25 light years, adds up to billions of individual impacts. The cumulative effect is erosion. The forward-facing surfaces of the ship are being continuously sandblasted by particles too small to see, each one excavating a tiny crater, each one degrading the surface material by a microscopic amount. Over years, this erosion changes the optical, thermal, and structural properties of every exposed surface. Radiator panels lose emissivity, sensor windows become pitted and cloudy, structural panels thin, and the erosion is not uniform. It concentrates on whatever faces the direction of travel, meaning the ship's forward shield, its primary antenna, its navigation sensors, and any thermal protection on the leading edge all absorb the worst of it. Laboratory simulations of dust, impacts at interstellar relevant velocities, conducted as part of research associated with the breakthrough Starship project and related studies, have confirmed that even micrometer scale grains at a fraction of light speed can cause significant surface damage. For larger grains, the concern shifts from erosion to penetration. A grain 100 micrometers in diameter, still far smaller than a grain of sand, striking at 10% of light speed, carries roughly 500 joules of kinetic energy, comparable to a 9mm handgun round, but concentrated into a point of impact smaller than a pinhead. If even a single particle of that size impacts a pressurized module, the result could be a hull breach. The probability of encountering such a particle on any given day is extremely low. But the probability calculated across billions of kilometers and decades of travel is not zero. And on a ship where a hull breach cannot be repaired by anyone outside, a non-zero probability is a sentence hanging over the crew for the entire mission. There are mitigation strategies. A forward-facing shield, sometimes called a dust shield or a Whipple bumper, can absorb impacts and distribute the energy before it reaches the pressure hull. The shield itself would be sacrificial, designed to erode so that the hull behind it does not. But a sacrificial shield that is being consumed over 40 years of travel must be thick enough at launch to last the entire journey. And its mass adds to the same rocket equation problem that radiation shielding creates. Every gram of protection is a gram that must be pushed to interstellar velocity. The ship endures. It takes the radiation. It takes the dust. Its surfaces degrade, its shielding thins, its forward sensors accumulate pitting that gradually reduces the resolution. And all of this is happening while the internal systems are simultaneously aging, wearing, and drifting toward their own failure thresholds. The external environment attacks the outside of the ship. The internal environment stresses the inside. And the crew exists at the intersection, absorbing both. The question of repair deserves concrete attention, because the script of every Starship narrative includes a scene where a crew member fixes something, and the unspoken assumption is that fixing things is always possible if the crew is skilled and determined enough. That assumption does not survive contact with the reality of maintenance in interstellar space. Start with interior repairs, the easier category. A pump motor fails in the water recycling system. The crew has a spare. They power down the affected loop, drain the relevant section, remove the failed motor, install the replacement, refill, pressurize, and test. This is hard work in a confined space with limited tools, but it is achievable. The problem is what happens the second time the same model of motor fails. 5 or 10 years later, and the spare has already been used. Now the crew must either repair the failed motor using its own components, which may not be possible if the failure mode is a burned winding or a cracked housing, or fabricate a replacement from raw materials. Fabrication aboard a spacecraft requires machine tools, feedstock, electrical components, and the expertise to design and build a functional motor in an environment where precision machining is complicated by vibration, atmospheric contamination, and the limited range of materials available. These are skills that can be trained. They are not skills that can be guaranteed across every possible failure mode for every possible component for 40 years. Now consider exterior repairs. The ship's radiator panels, forward shielding, antenna arrays, and sensor packages are all exposed to the interstellar environment. When they degrade or fail, someone must go outside. An extravehicular activity in interstellar space is unlike any spacewalk ever performed. There is no structure to anchor to, no robotic arm, no magnetosphere providing even partial radiation shielding. The crew member is exposed to the full flux of galactic cosmic rays for the duration of the repair, accumulating a radiation dose that would be considered excessive for an entire mission by current standards, compressed into hours. They are also exposed to the micrometeoroid flux, wearing a suit whose outer layers are the only barrier between their body and particles carrying the kinetic energy of small explosives. If the ship is rotating to provide artificial gravity, the exterior environment is even more dangerous. The crew member must navigate a structure that is spinning, where every movement away from the rotation axis changes the effective gravity they experience, and where a detached tether means being flung into the void with no possibility of retrieval. The ship cannot stop its rotation for a repair without disrupting the artificial gravity for everyone aboard, a procedure with its own physiological consequences and operational risks. If the ship is not rotating, the repair takes place in microgravity, which presents its own challenges. Tools drift, bolts float away. The human body is not optimized for precise mechanical work without the anchoring effect of gravity. Every action produces an equal and opposite reaction that must be managed. Fluid systems behave differently. Lubricants and sealants do not flow the way they do on Earth. And every exterior repair requires equipment. Replacement panels, sealant compounds, thermal coatings, spare antenna elements. Each of these is a consumable that was packed before launch and that diminishes with every use. A repair performed in year 5 means one fewer repair possible in year 35. The crew must balance the urgency of a current repair against the probability of needing the same resource for a more critical repair in the future. A calculation made under uncertainty that compounds with every passing year. There's one more dimension to the repair problem that is rarely discussed: skill atrophy and skill loss. The crew was trained before launch. They are highly capable people, selected for their breadth of expertise. But expertise in a specific repair procedure is perishable. A crew member who performed a complex reactor maintenance operation during training on Earth may not perform it again for 15 years. When the need arises, they are working from memory, from documentation, and from a body that is older, less dexterous, and operating under the cognitive effects of radiation and confinement. If the crew member with the relevant expertise has died, the skill may exist only in the ship's technical manuals, interpreted by someone who has never performed the procedure and who is learning it for the first time under conditions where failure is not a training opportunity but a survival emergency. The ship's repair capacity is not a fixed quantity. It is a declining one. It declines as spare parts are consumed, as tools wear, as materials are used, as crew members age and die, and as the cumulative effects of radiation and isolation erode the human capabilities that make repair possible. The ship launched with the maximum repair capacity it will ever have. Every day after launch, that capacity is slightly less than it was the day before. And the ship's need for repair is moving in the opposite direction, increasing as components age and the environment continues its assault. Now, consider what happens to the crew's connection to everything they left behind. Not emotionally, although that matters enormously, but operationally. Communication with Earth is the crew's last link to the collective knowledge, engineering expertise, and decision-making infrastructure of the entire human species. On every previous space mission, that link has been a lifeline. Apollo 13 survived because of it. The International Space Station functions because of it. Mars missions are designed around it. Even with the 22-minute delay at Mars's farthest point from Earth, mission controllers can still participate meaningfully in troubleshooting, planning, and decision support. On an interstellar crossing, that link dissolves. The delay math was established earlier, and it is worth feeling again from the operational side. The crew discovers a problem with the carbon dioxide scrubber. They describe it in a message and transmit it toward Earth. Then they wait. Not hours, not days, months. When the answer finally arrives, it addresses a version of the problem that may no longer exist, because the system has been degrading the entire time the signal was in transit. The engineers who wrote the response were solving yesterday's crisis. The crew is living inside tomorrow's. And if the problem worsened during the delay, the advice is not just late, it is obsolete. As the mission deepens, the delay widens from months to years, and the nature of the link changes. It stops being communication and becomes something closer to archaeology. Messages from Earth arrive carrying news of a world the crew is no longer part of. Political systems have changed. Cultural references have shifted. People the crew once knew have aged, moved, or died. A crew member who sends a birthday message to a child will receive a reply from a young adult they have never met as that person is now. The voices from home become voices from another era. And the crew must absorb this temporal dislocation while continuing to operate a machine that depends on their focus, their cohesion, and their will to continue. The psychological literature on long-duration isolation is extensive, and the conclusions are not comforting. NASA's Human Research Program has identified behavioral health risks as among the most serious and difficult to mitigate threats to long-duration spaceflight. The evidence comes from multiple sources: Antarctic winter-over expeditions, submarine deployments, analog habitat studies, and 2.5 decades of continuous occupation on the International Space Station. The Mars 500 study, conducted between 2010 and 2011, confined 6 male volunteers in a 550 cubic meter chamber for 520 days to simulate a round-trip mission to Mars. The crew experienced significant inter-individual differences in psychological response, but the overall pattern included increased sleep disruption, decreased activity levels, depressive symptoms, and interpersonal tension that worsened as the mission progressed. One crew member spent most of the latter half of the mission in a state of chronic sleep disruption that left him functionally impaired for large portions of the day. Another withdrew socially to a degree that researchers flagged as concerning. 520 days, roughly 1 year and 5 months. An interstellar mission at 10% of light speed to Alpha Centauri would last approximately 15,700 days, 30 times longer than the Mars 500 simulation. And the simulation had a crucial psychological advantage that the real mission would not. The crew knew they could leave. The door to the chamber existed. The knowledge that the outside world was right there, separated by a wall, provided an unconscious safety net that shaped every psychological response inside. On a starship, there is no door. There is no wall between the crew and home. There are light years of vacuum, and the only way out is forward, and forward is decades away. The technical term for this condition is inescapable confinement. Research on human responses to situations perceived as inescapable shows a consistent pattern. Learned helplessness, a psychological state in which individuals stop attempting to improve their situation because they believe no action can change the outcome. Emotional flattening, where the range and intensity of emotional responses narrows as a protective mechanism against sustained stress. Cognitive tunneling, where attention narrows to immediate concerns and the capacity for long-term planning, creative problem solving, and flexible thinking diminishes. And interpersonal erosion, where the small frictions of daily life in a confined group, which are manageable over weeks or months, calcify into entrenched conflicts over years. There are specific psychological phenomena documented in isolation research that deserve closer attention, because they map directly onto the timeline of an interstellar crossing, and they intensify the compounding dynamics that define the Coffin equation. The first is called the third quarter phenomenon. It has been observed consistently across Antarctic winter over expeditions, submarine deployments, and confined habitat studies. Roughly 3/4 of the way through a mission of known duration, crew morale undergoes a sharp decline. Motivation drops, irritability spikes, depression deepens. The pattern is robust enough to appear across different cultures, different crew compositions, and different mission types. Researchers believe it occurs because the mission's novelty has fully dissipated, while the end remains too distant to provide motivational pull. The crew is stranded in a psychological no man's land, too far from departure to draw energy from its excitement, too far from arrival to draw energy from its anticipation. On a mission lasting 520 days, The third quarter point arrives around day 390. A difficult week. On a mission lasting 43 years, the third quarter point arrives around year 32. Not a difficult week, a difficult era. Years of diminished motivation occurring precisely when the ship's systems are at their most degraded, the crew's bodies are at their most radiation damaged, and the reserves are at their lowest. The third quarter phenomenon does not cause system failure, but it reduces the crew's psychological capacity to fight system failure at the moment when fighting it matters most. The second phenomenon involves the loss of visual contact with Earth. Astronauts aboard the International Space Station consistently describe the experience of looking down at Earth as one of the most psychologically sustaining aspects of their missions. The overview effect, the emotional and cognitive shift that comes from seeing the planet as a whole, has been reported by nearly every astronaut who has experienced it. It provides a sense of connection, of meaning, of home. On a starship, Earth will be visible as a bright point of light for the first weeks or months. Then it will dim. Eventually, it will be indistinguishable from the surrounding stars without telescopic assistance. The crew will pass a threshold, unmarked by any instrument but felt by every person aboard, when they can no longer see home with their own eyes. That moment has no analogue in human experience. No explorer in history has ever been unable to look back at the land they left and see something. Sailors could turn and watch the coast recede. Antarctic expeditioners could step outside and see the sky above the same planet their families lived on. An interstellar crew will look out the window and see nothing that connects them to anything human. Only stars. Only the same stars they will see tomorrow, and the day after, and the year after, and the decade after. The visual monotony of interstellar space is total. There is no horizon, there is no landscape, there is no change. The third phenomenon is grief. On a mission lasting decades, people will die. Not necessarily from system failure or radiation. From the ordinary causes that claim human lives at every age. A cardiac event, a stroke, an accident during maintenance, an infection that the medical bay cannot resolve. And when a crew member dies in a group of 12, the consequences are not merely emotional, they are operational and ecological. Operationally, the dead crew member's skills and knowledge are gone. If that person was the primary engineer responsible for the reactor cooling system, or the only crew member with advanced surgical training, or the most experienced agricultural specialist aboard, their death creates a capability gap that cannot be filled. The remaining crew must absorb the dead person's responsibilities on top of their own, while simultaneously processing grief in an environment that offers no escape, no memorial infrastructure, no community of support beyond the handful of faces they have been looking at for years. Ecologically, the body presents a problem that is uncomfortable to discuss, but impossible to ignore in a closed-loop system. The ship is a sealed biosphere. Every kilogram of mass aboard is part of the resource cycle. The protocols for handling human remains in an interstellar context have not been established, but every option carries weight. Burial in space means the permanent loss of the mass and nutrients the body contains from the ship's closed loop. Retention and recycling is technically logical, but psychologically devastating. Storage requires space, energy, and containment that the ship may not be able to spare. There is no good answer. There is only a set of bad options that the crew must choose among while grieving. The fourth phenomenon is the erosion of meaning. Human beings sustain effort through purpose. Every long-duration mission in history has been anchored by a sense of significance that justifies the hardship. Antarctic expeditioners endure the cold because they are gathering data that matters. Submarine crews endure confinement because they are serving a national defense mission. Astronauts endure the risks of spaceflight because they are expanding the frontier of human knowledge. In each case, the purpose is reinforced by an external community that values and acknowledges the sacrifice. An interstellar crew begins the mission with intense purpose. They are the first humans to travel between stars. The significance is self-evident, but significance, like every other resource aboard the ship, is subject to erosion over time. By year 15, the departure is ancient history. By year 25, the crew's connection to the civilization that launched them has become abstract. The messages from Earth arrive years late, describing a world the crew can barely recognize. The mission's significance, which was originally validated by an entire planet's attention, must now be sustained entirely from within, by people who are tired, confined, and physiologically compromised. Sustaining meaning under those conditions is not a matter of willpower. It's a psychological engineering problem, as difficult as any mechanical one aboard the ship, and it has received a fraction of the research attention. A crew experiencing learned helplessness is a crew that stops reporting problems. A crew experiencing cognitive tunneling is a crew that misses the slow onset failures that define life aboard the ship. The gradual degradation of a filter membrane, the fractional decline in reactor output, the barely perceptible change in atmospheric composition. A crew experiencing interpersonal erosion is a crew that can no longer coordinate effectively during an emergency. Because the trust and communication required for coordinated action have been worn away by years of unresolvable tension in a space they cannot leave. And here is the element that transforms all of these individual threats into something qualitatively different from anything faced on a shorter mission. They compound, not sequentially, not one at a time in a neat and manageable order, but simultaneously, continuously, and interactively. Radiation degrades the crew's cognitive function. Degraded cognitive function reduces the crew's ability to detect and respond to system failures. Undetected system failures degrade life support. Degraded life support increases physiological stress on the crew. Increased physiological stress amplifies the psychological effects of confinement and isolation. Amplified psychological effects further reduce the crew's operational capacity. Reduced operational capacity leads to maintenance backlogs. Maintenance backlogs allow mechanical degradation to accelerate. Accelerated mechanical degradation increases the frequency and severity of system failures. And each new failure occurs in a context where the crew is less capable, the ship is less functional, and the reserves are smaller than they were before. This is a positive feedback loop in the engineering sense, a cycle where each output feeds back into the input in a way that amplifies the effect. In stable systems, negative feedback loops counteract this kind of runaway process. A thermostat detects rising temperature and activates cooling. A pilot detects a roll and applies corrective input. On Earth, in low orbit, in the inner solar system, the feedback loops available to a crew include mission control, resupply, evacuation, and the physical proximity of people and infrastructure that can intervene. In interstellar space, those counterbalancing loops are gone. The only negative feedback available is the crew's own skill, resourcefulness, and endurance. And those resources are themselves being depleted by the very processes they are trying to counteract. There is no single moment when the ship crosses from safe to doomed. There is no alarm that sounds, no red light that illuminates, no dramatic event that marks the transition. Instead, there is a slow convergence. The margins shrink from every direction at once. The water recovery rate drops a fraction of a percent per year. The reactor output declines a fraction of a percent per year. The crew's cognitive baseline shifts downward a fraction of a percent per year. The hull's forward shielding thins by micrometers per year. The communication delay grows by months per year. And the reserves, the spare parts, the backup filters, the emergency water, the contingency food stores, all draw down by increments so small that no single withdrawal feels dangerous. But the trajectory is visible in the aggregate. If you plotted every one of these declining curves on a single graph, you would see them converging. Not toward a wall, not toward a cliff, but toward a region of the graph where the lines cross each other, where the demand on each system exceeds the capacity of that system, and where the crew's ability to compensate is no longer sufficient to bridge the gap. That region has a name in systems engineering. It is called the point of irrecoverable departure. It is the moment past which no intervention available to the crew can restore the system to a sustainable operating state. Before that point, heroic effort can buy time. After it, the physics are final, and the crew may not know when they cross it. That is perhaps the most harrowing aspect of the entire problem. The point of irrecoverable departure is not marked by anything visible. It is defined retrospectively, identified only in the analysis after the fact. When someone traces the curves backward and identifies the moment when the last remaining option closed. On a starship, there is no after-the-fact analysis performed by anyone outside. There is only the crew inside the ship, watching the margins narrow, knowing the margins are narrowing, and understanding with increasing clarity that the vessel carrying them toward a star is also the vessel from which they cannot escape if the narrowing does not stop. Every threat described in this story so far, radiation, dust erosion, communication loss, psychological deterioration, system degradation, exist on its own terms and has been studied independently. But they do not strike independently. They strike together constantly for decades, and each one makes every other one worse. The ship does not face a single enemy, it faces a siege, and the siege does not need to breach the walls. It only needs to outlast the supplies. The walls are still holding, the air is still breathable, the lights are still on, the crew is alive, and the destination star is closer today than it was yesterday. But closer is a relative term when the journey is measured in decades, and the ship is now deep in the crossing, far from the star it left, and far from the star it is approaching, suspended in a region of space where no human signal has ever traveled, and no human hand can reach. The ship is alone. The crew is alone. And the distance that made this journey meaningful is the same distance that has removed every safety net ever devised by the species that built the ship. What that distance ultimately means, not for the engineering but for the crew, not for the systems but for the human beings sealed inside them, is the final question this story must answer. There is a moment in every thought experiment about interstellar travel that most people skip past without realizing they have done it. It is the moment between departure and arrival. Not the dramatic ignition of the engines, not the triumphant first glimpse of a new star growing brighter in the forward sensors. The moment in between, the decades of silence, The years upon years in which the ship is simply there, moving, existing, carrying its passengers through a darkness so total and a distance so vast that the word journey begins to feel wrong. A journey implies a path. A path implies landmarks, waypoints, signs that you're getting somewhere. An interstellar crossing has none of these. There is only the inside of the ship. There is only the machinery. There is only the crew. And there is only the knowledge, carried by every person aboard every single day, that the walls surrounding them are the only thing standing between life and the void. And that those walls are getting older. Everything described so far in this story leads to a single conclusion. Not a dramatic one, not a cinematic one, a quiet one. The Starship becomes a coffin, not because it is destroyed by some spectacular event, some collision or explosion or systems failure that kills everyone in a flash. It becomes a coffin because interstellar distance transforms the relationship between the ship and its crew from one of protection into one of confinement. And because inside that confinement, time does what time always does to closed systems. It degrades them, slowly, steadily, and without mercy. Let us walk through the chain one final time, not as separate categories, but as a single, unbroken sequence. Because the sequence is the point. The individual threats matter, but what makes an interstellar starship uniquely dangerous is the way those threats connect into a cascade that has no external circuit breaker. A crewed starship leaves Earth. It accelerates over a period of months or years until it reaches its cruising velocity. The engines go quiet. The ship enters the coast phase. From this moment forward, the vessel is ballistic. It is moving through interstellar space at a significant fraction of the speed of light, and it will continue moving at that speed until the deceleration phase begins, years or decades later. During the coast phase, the ship cannot stop. It cannot turn around in any practical sense, because the fuel required to decelerate, reverse course, accelerate back toward Earth, and then decelerate again at Earth would require an energy budget many times larger than the original mission profile. The ship is committed. The crew is committed. The only direction is forward. With every passing day, the distance between the ship and Earth increases. With every passing day, the communication delay grows longer. With every passing day, the possibility of rescue recedes, not gradually in the way that a shoreline recedes from a swimmer. Absolutely, in the way that a door closes and locks. By the time the ship is 1 light year from Earth, the door is already sealed. No vehicle exists or is being built that could catch the ship, match its velocity, deliver supplies, and return. The crew knows this. They knew it at launch. They accepted it. But knowing a thing intellectually and living inside that knowledge for 10,000 consecutive days are not the same experience. Meanwhile, the ship ages. Every component aboard has a design life. That design life was estimated on Earth, tested under conditions that approximated the mission environment, and extrapolated across timelines no test facility could actually run. No one has tested a water recycler for 40 continuous years in interstellar radiation. No one has run a fusion reactor for 4 uninterrupted decades in the vibration environment of a crewed vessel at cruise velocity. The design lives are projections. They are informed projections made by brilliant engineers using the best data available, but they are projections. And the gap between a projection and a reality is measured in all the things the projection did not account for. The trace contaminant nobody modeled, The material interaction nobody tested. The failure mode that only emerges at year 27 under conditions that only exist inside a starship crossing between stars. The systems degrade. The water recycler loses a fraction of its recovery efficiency. The air system's catalytic beds lose a fraction of their reactivity. The power system's output decreases as reactor fuel depletes, and structural materials embrittle under sustained neutron flux. The thermal radiators lose emissivity as their surfaces erode from micrometeoroid impacts and radiation exposure. The lighting in the agricultural module dims as diodes age. Each of these losses is small. Each, measured on the scale of a single day, is invisible, but they accumulate. And they accumulate in a system where every function depends on every other function, so that the degradation of any one system increases the load on or reduces the supply to every connected system. This is the compounding principle, not one failure. 1,000 small failures, each feeding the next, each slightly reducing the ship's capacity to sustain the lives inside it. And because the ship is sealed, because nothing enters from outside, the trend only moves in one direction. There is no resupply to reverse the water loss. There is no maintenance team to replace the reactor's embrittled components. There is no shipyard to recoat the radiator panels. The crew does what it can with what it has. They improvise. They rebuild. They cannibalize non-essential systems for parts. They accept lower performance in one area to preserve function in another. They ration. They adapt. But adaptation has limits. Every improvisation consumes a resource that cannot be replaced. Every cannibalized system is a system that no longer performs its original function. Every reduction in one capability increases the pressure on the capabilities that remain. The crew is not solving problems. They are managing a decline. And the decline is not a failure of their effort or their ingenuity. It is a consequence of physics. Closed systems trend toward entropy. The second law of thermodynamics does not grant exceptions for courage. While the ship degrades from within, the crew degrades alongside it. Galactic cosmic rays have been striking every cell in every body aboard since the ship left the heliosphere. The cumulative dose rises year by year. The biological effects are not immediate, but they are inexorable. DNA damage accumulates. Repair mechanisms become less efficient with age. The risk of cancer climbs. Cardiovascular tissue weakens. And the cognitive effects, the subtle erosion of memory, attention, and executive function proceed at a rate that the crew may not consciously detect, because the decline is gradual enough to feel like normality shifting, rather than capability vanishing. A crew with impaired cognition makes more errors. More errors mean more system misconfigurations, more maintenance oversights, more delayed responses to warning indicators. Each error, however small, contributes to the overall degradation of the ship's condition. The crew is the ship's last line of defense against system failure. And that line of defense is being weakened by the same environment that is weakening the ship. Add the psychological dimension. The crew has been confined in a pressurized volume, the same rooms, the same corridors, the same faces, for years. The monotony is not an inconvenience. It is a grinding, relentless psychological force that erodes motivation, social cohesion, and the sense of purpose that makes sustained effort possible. Interpersonal conflicts that would be minor irritations in an environment where people can take a walk, visit a friend, or simply leave the room become chronic sources of stress when there is no room to leave to. Sleep disruption, documented in every long-duration isolation study ever conducted. compounds the cognitive effects of radiation, reducing the crew's functional capacity below what either factor would produce alone. And beneath all of this, running constantly in the background of every crew member's mind, is the knowledge. The knowledge that no one is coming. The knowledge that the nearest human being who could help is receding at a rate measured in light months per year. The knowledge that if the carbon dioxide scrubber fails beyond the crew's ability to repair it, there is no emergency protocol that ends in survival. There is only the atmosphere inside the ship. And when the carbon dioxide concentration rises past a certain threshold, consciousness narrows, then fades, then ends, and the ship keeps flying. Silent, dark, a metal shell carrying remains toward a star that the people inside will never see. This is what the Coffin equation describes. Not a single catastrophic event. A convergence. A slow, quiet convergence of declining curves, each one representing a system or a capacity that is slightly less functional today than it was yesterday. All of them moving in the same direction, all of them interconnected, and all of them operating inside a sealed vessel that cannot be opened, cannot be resupplied, and cannot be reached by anything or anyone from outside. The word coffin is not chosen for dramatic effect. It is chosen because it is structurally accurate. A coffin is a sealed container that holds human beings who can no longer help themselves. A starship in the late stages of compound system failure is exactly that. The crew is inside. The hull is intact. The ship is still moving. But the capacity to sustain life is narrowing toward zero. And the distance to any alternative is measured in light years, and there is no action available to anyone, inside or outside the vessel, that can change the outcome. The first interstellar starship will not fail the way spacecraft fail in movies. There will be no explosion, no dramatic decompression, no visible moment of destruction. It may fail the way closed systems fail in the real world. A water recycler whose membrane degrades 1% per year until in year 34, the recovery rate drops below the threshold required to maintain the crew's hydration. A reactor whose output decreases so gradually that no single month's data looks alarming, but whose cumulative decline, plotted across a decade, describes a line that intersects the minimum power requirement for life support in year 38. A crew whose collective cognitive function has shifted enough that the maintenance error rate, invisible in any individual task, produces a statistical increase in system faults that accelerates the degradation already underway. None of these failures triggers an alarm on the day it begins. Each one is quiet. Each one is patient. Each one waits for the others to converge. Because it is the convergence, not any single thread, that is lethal. And by the time the convergence becomes visible, the ship is too far from help, and the systems are too far degraded, and the crew is too far diminished for recovery to be possible. This is the truth that the heroic image of the Starship conceals. The ship is not just a vehicle, it is the entire world. It is the atmosphere, the water supply, the food source, the hospital, the factory, the shelter, and the only barrier between its inhabitants and instant death. On Earth, those functions are distributed across a planet. In low orbit, they are distributed between the spacecraft and the ground infrastructure supporting it. On a starship, they are concentrated in a single structure, and that structure is the only one of its kind within light years. If it fails, there is no second one. If its atmosphere becomes unbreathable, there is no outside air. If its water becomes unpotable, There is no river, no well, no rain. The ship is both protector and prison. The hole that keeps the vacuum out is the same hole that keeps the crew locked in. And the distance that makes the journey meaningful, the distance that represents humanity's greatest ambition, the distance that separates one star from another across the indifferent expanse of the galaxy, is the same distance that seals the trap. Because distance is not just a number, it is the removal of options. At 1 light year from Earth, the option of real-time communication is gone. At 2 light years, the option of timely advice is gone. At 3 light years, the option of anyone on Earth even knowing about a crisis before it has resolved itself, one way or another, is gone. The distance strips away every safety mechanism that human beings have ever relied on, layer by layer, light month by light month, until the crew is left with nothing but their own hands, their own minds, and whatever the ship still has to give them. There is a profound asymmetry in this arrangement that deserves to be named plainly. Launching the ship is a collective act. Thousands of engineers, billions of dollars, decades of research, the combined effort of institutions and nations and generations of accumulated knowledge all contribute to the moment of departure. But surviving the crossing is a solitary act. Once the ship leaves, the collective cannot reach it. The knowledge of thousands of engineers is only useful if it can be transmitted, received, understood, and applied by the handful of people aboard. The resources of an entire planet are only useful if they can be delivered, and they cannot be delivered across light years. The crew is the beneficiary of all that collective effort at launch, and then the crew is alone. Everything after departure is endured by the few, in silence, in confinement, in a machine that is slowly, imperceptibly running down. This is not an argument against interstellar travel. It is not a case for staying home. It is a recognition that the vehicle intended to carry human beings to another star is, by the physics of the situation, also the vehicle most likely to become their final resting place if anything goes wrong. And anything is a vast category when the mission duration is measured in decades, and the margin for error narrows with every passing year. The unsettling part is not that the Starship could fail. Every spacecraft can fail. Every mission carries risk. Astronauts accept risk every time they climb into a capsule, and the bravery required to do so is genuine and admirable. The unsettling part is the nature of the failure. It is not sudden. It is not dramatic. It is not the kind of failure that produces a story of heroic struggle against overwhelming odds. It is the kind of failure that produces a long, quiet decline in a sealed room that no one on the outside can enter, ending not with an explosion, but with silence. A ship still flying, its trajectory unchanged, its hull intact, its engines cold, its corridors dark, its air depleted, its crew gone. A vessel that crossed the distance between stars and somewhere in the crossing became something else. Not a vehicle, not a habitat, a sarcophagus, sealed by the same engineering that was meant to sustain life, and carried forward by the same momentum that was meant to deliver it. This is the image that the title of this story names, and it is an image that anyone serious about interstellar travel must confront honestly. The first ship that attempts the crossing will not carry tourists. It will carry people who understand, fully and without illusion, that the machine they are boarding may become the machine they die inside. They will board it anyway. That is what makes them extraordinary. But the honesty to name what the machine is and what it could become is owed to them and to every person who will watch them leave. The stars are real. The distance is real. The The dream of reaching another sun is among the most magnificent ambitions our species has ever conceived. And the ship that carries that dream will be the most remarkable, most complex, and most audacious piece of engineering ever built by human hands. It will also be the most dangerous place a human being has ever voluntarily entered. Not because space is hostile, although it is. Not because the engineering is flawed, although it will be imperfect. But because distance does something to failure that no other variable in the equation does. It makes failure permanent. On Earth, failure is an event. You recover, you rebuild, you try again. In low orbit, failure is an emergency. You evacuate, you repair, you send a new crew. On a starship crossing the interstellar void, failure is a condition. It sets in, it deepens, it compounds, and it does not end, because there's nowhere to go and no one to call, and no second chance waiting on the other side of a door. The ship that leaves for another star will carry everything that is best about our species. Our curiosity, our defiance, our refusal to accept the limits the universe imposes. It will carry our science, our engineering, our art, and our hope. And it will carry our vulnerability, our biological fragility, our dependence on systems that wear out, our need for air and water and food and warmth and each other. And it will carry all of these things into a place where there is no rescue and no return, where every margin is finite and every failure is final. The ship will be magnificent. It will also be a coffin for anyone inside it if the margins run out. And the margins will be thinner than most people imagine, because 40 years is a long time for a machine, and an eternity for a closed system. And the distance between stars is not just a measure of space. It is a measure of how alone the crew will be when the margins reach zero. That is the real reason a starship may become a coffin. Not because interstellar travel is impossible. Not because humans are too fragile. Not because the engineering cannot be done. But because the distance transforms the ship from a vessel into a sealed world, and sealed worlds do not forgive. They do not offer second chances. They do not open when you knock from the inside. They hold you and they carry you, and they keep you alive for exactly as long as their systems can sustain you. And when those systems can no longer sustain you, the ship keeps flying. The stars keep burning. The distance keeps growing between the ship and the world that built it. And the silence, when it comes, lasts forever. Because there is no one close enough to hear it, and no one fast enough to reach it. And the ship, still intact, still moving, still pointing toward a star it may one day reach, carries its crew forward into the dark. Not as explorers arriving, but as passengers who departed and never came back, sealed inside the most extraordinary machine humanity ever built, sealed inside their own ambition, sealed by distance, by time, and by the quiet, irreversible arithmetic of a closed system that finally, after years or decades of holding the line, could not hold it any longer. The stars do not care. They burn whether we reach them or not. But the people who choose to try will deserve the most honest accounting of what they face that our species is capable of giving them. This is part of that accounting. The rest is engineering. And the engineering has never been more important, or more difficult, or more worthy of our attention. Because the ship will be built. Someone will build it. And when it leaves, everything it carries, every life, every hope, every molecule of air and water and courage, will depend on whether the engineers got the margins right. Not for a day, not for a year. For the crossing, the whole crossing, every hour of it, every light year of it. And if they did not, the stars will receive the ship anyway, and the ship will arrive as something other than what it was when it left. Not a vessel, not a home, a marker, a monument to the distance between ambition and survival, a coffin carrying the bravest people who ever lived, delivered by their own momentum to a place they dreamed of reaching, and sealed by the same physics that carried them there. That is the equation. Distance plus time plus a closed system plus no rescue equals a margin that only moves in one direction. And when the margin reaches zero, the coffin is complete